Di Filippo from the Institute in Frankfurt, and we will talk about quasi and singular paradigm for black holes.
Okay. Thank you, Alessia. Thank you, and also congratulations to Luca for this conference.
Okay, sure.
Okay, so quasi and singular paradigm for black holes. I would like to start by just asking you to picture orbiting around a black hole, and I'm sure that you will not have any problem in picturing what's going to happen. Of course, it depends a lot on how far away you are from the black hole. It depends on the mass and the speed of the black hole. We don't know exactly the astrophysics, so there will be a lot of uncertainty due to astrophysics. But more or less, we know what to expect. And we know what to expect both because we have a very good theory to describe it, and because we have a lot of experimental data now. And yesterday we had a very nice talk from Alexander Bonanno describing the gravitational waves, and also we have a very electromagnetic observations. So, no surprises there. Now we get a little bit closer to the horizon. We don't even need to get in at this stage, and I don't even want to enter into what horizon means. I will not talk about event horizon, tracking horizon, dynamic horizon, or time horizon. And this is just closer to the black hole, let's say. And in this region of space-time, either inside or outside, the observation become less helpful because it's very difficult to form your new horizon scale. But we still have a very good theory of gravity to describe it. So we will still not have any problem in picturing what's going to happen, depending on how big is the black hole, whether or not you will survive the kind of forces, or this kind of issue. You can all picture what is going to happen. But then as we continue falling in, the situation is very different. The situation is very different, and I take here a picture from the famous paper by Penrose in 1965. Which was the first result telling us that we will unavoidably reach the end of predictability of the theory. So the singularity, or anyway, actually incompleteness. So this means that we no longer have a theory. I remove the Einstein equation here. We do not have any information, and we really don't know what's going to happen. And whenever you tell your friends that you work on black hole physics, they are going to ask you, so what happens if the fall is of the core? And my answer is, I don't know, because the theory is not working. The theory of gravity is not working. And I think in the first day of the conference, I think it was Guillaume, I'm not sure, he mentioned usually a theory tells you, gives you hints on where it's going to break down, but general relativity is really screaming that it's going to break down inside the code. However, unfortunately, general relativity also does a very good job in hiding these problems, which we can summarize, for instance, by the weak cosmic censorship conjecture, which is a conjecture put in place so that we can make sense of general relativity outside the code. It's telling us that all the singularities and all the effects of singularity regularization, all the singularity will be eaten from asymptotic observers by event horizon, in this case we call it event horizon. So as long as we are outside, we don't need to worry about that. However, even though this is definitely a very difficult place to go and look for something, like it's impossible inside the black hole, but even near the horizon region is very difficult to go. I would say that while this is a very, very good, it could be a good practical approach to assume that whatever is the effect of singularity is hidden from us, and we start looking for a full theory of gravity, and once we find it, we try to understand what's going on. I think there is also use in studying what are the possibilities that arise singularity regularization, what is the thing that we might expect. And in principle, in particular, there are some questions here that are interesting to think about. The first one is whether or not modifications to the R will be limited within the horizon. And in order to understand that, we need some framework. So what framework can we use? Then we can ask what are the possibilities, and also if we want to push it a lot, is whether or not there are phenomenological implications. And today I'm going to talk about more or less these questions. And this is a good reference to start looking at. It is a good reference with several people in which we try to lay the stage and to write down in a more or less pedagogical way what are the possibilities, what are the implications, and what are the open questions. So if you open this paper, you will find a set of questions that, in our opinions, are the most important question in the topic at the moment, and discussion on these points. Now, of course, I'm not going to go through this all these questions. I will take very, very few of them, which are the ones that I work the most. Of course, this is a lot of people here. I will mostly focus on my own work and mostly collaboration with these first 4 authors. And particularly, I will mostly talk about instabilities, because I think they can teach us a lot. But let's start from the beginning, what does it mean to be non-singular, what is the framework that we're going to use, and what are the possibilities. So, the first point, I'm talking about non-singular paradigm. What does non-singular mean? And you see there are several people in that paper. We were not completely agreeing on what does non-singular mean. So there was the first step was already some disagreement. But I would say that we can give these 2 requirements, and then depending on your taste, you can drop one or the other. But the first one is just completely the physical trajectories. For instance, geometric completeness. We want that the theory is predictive for every observer, for every causal observer, not only the ones staying outside the course, also for the one referring. And then the other one is finiteness of physical observables. So we want to avoid things like curvature singularities. And now, which framework do we want to use? Now, standard framework is to keep the kinematics of geometry, so to keep the meaning of pseudo-Riemannian manifold. So we still describe our theory in terms of space-time. And of course, this can, and this is the approach that we're going to use. But of course, there are at least 2 possible caveats. The first one, I think everyone can immediately think about it, is that it's possible that in some situation we cannot describe physics in terms of smooth manifold. We need something like discrete geometry or simply discreteness of our description. And this is, of course, one possibility that it's happened in several quantum gravity approaches. But still, it's still good to accept this framework, to look at the implications, and then see whether or not we want to doubt this possibility here at the end. And also, it's possible that maybe the smoothness of space-time breaks down in some region, but we can find something effective in that region, and most of the space-time is still going to be smooth, and still this might give us some interesting conclusion. Now, the second caveat is that we might have some given theory that might be a good theory of gravity that could produce non-singular space-time, but only for reasonable initial conditions, while other initial conditions might still be problematic. And one example is, for instance, quadratic gravity, whether or not you like it because of the ghost, for instance. It is a renormalizable theory of gravity, but still, if we look at the vacuum solution, and we also have a work with Luca, in which we look at one very idealized spherical collapse model. If you look at this solution, these are singular. However, this might not be a problem because maybe these singular solutions are not realized in nature, and we might need to look at more generic collapse to understand whether or not a theory is problematic or is acceptable. So we need to keep in mind these 2 caveats, and then we can go back later, but this is the framework we're going to use, a geometric dynamic theory. And if we do this, we can give a classification of spacetimes. Here, a classification of spacetimes that satisfy the criteria that we want. We want something that mimics sufficiently well a black hole spacetime to pass the current test, but also something which is non-singular. And here I have some possibilities. You can look more details here. And particularly, we are not really going to discuss about wormholes today, but we should keep in mind that these exist and these are an interesting possibility. We're going to look at the other two classes that I'm going to describe right now in more details. So here is just a pictorial representation. On one side, you have a classical black hole in which you have singularity, and you also have an horizon. So the singularity should be on the horizon. The first possibility, the one we call regular black hole, is a very simple and minimal modification of black hole spacetime, in which you have a regular core instead of a singularity. And you can show that this introduces the need of a second inner horizon. And then you have some more exotic possibilities, which are horizonless objects, in which you do not have an horizon anymore. This is just a surface or a boundary of your object, but no horizon. And here I'm also showing other things like light rings, or that we are going to show you why these are relevant later on. And this is just to provide the simplest example you can imagine: static spherical symmetric spacetime and a very specific choice. We can consider this geometry over here, in which we have two parameters. One is the mass of the spacetime, and the other one is this L parameter, which is a regularization scale. Now, if you put this L to 0, you just get Schwarzschild, and for a larger value of L, non-zero value of L, you get something which is non-singular black hole. The small, for very small L, this looks very, very much like Schwarzschild at higher distances, and then greater is L, the bigger deviations. What am I plotting here? Here I am plotting as a function of L and R. I am plotting in red the outer horizon. In green, this line here, this is the inner horizon. So you can see for L equals 0, we have one single horizon at 2m. This is partial solution. And for any non-zero value of L, we get a second horizon in the interior of the object, in the core of the object. And this is just the regular black hole class I was showing you before. So we have outer and inner horizon. This yellow line here, this is just the standard light ring in Schwarzschild. That for L equals 0, this is at 3m. For different value of L, this is just move a little. And this blue line is an extra light ring that arises once the value of L is large enough so that you do no longer have an horizon. So if you push L up to this value, the outer and inner horizon merge, and you get an object which is horizonless. It does not have any horizon, but you will have the two light rings. And why am I putting a light ring? And we will see it later on. Okay, so this is just the simplest geometry we can think of, but this is just for the sake of having a simple picture here. We can. But what I want to say is going to be more generic than this single parameterization. To say that we mostly focus on instabilities today, and this is going to be probably surprising for some of you, because I'm saying that I am studying the kinematics of the theory, so I'm studying smooth space-time, but I'm not giving you 3D equations. So how can I ever talk about instabilities without giving 3D equations? And of course, there are going to be limitations, but let's see what can we say. And we start from the regular black hole class. So this shaded region of the parameter space, so the example before, in which we have both outer and inner horizon. And again, this is the static answers that we're considering. As I mentioned before, we're not considering wormholes. So this R square here is we could have a function of R that might have a minimum and will give us a wall of space-time. We are not considering that. So caveat that we do not have this normal, this is just its most generic spherically symmetric space-time. Why do we need to have two horizons? Well, the condition of the horizon is just f of r equals 0, this function f, and just by fixing its value asymptotically, and the value at r equals 0 is fixed by requiring the absence of curvature singularities, you can see that you need to have a double number of roots. And in particular, we can define the surface gravity in this way, and we will see that we have two different signs of surface gravity on the outer and the inner horizon. This is basically just the causal structure of a rising Northern black hole, except for the fact that r equals 0 is regular portion of space-time. The causal structure is the same. And we know that rising Northern black hole or black hole regenerativity, they are unstable what's called mass inflation, we will mention very soon. And we want to understand whether this is something more generic. But the problem is, as I mentioned before, we do not know the field equations of the theory. We will see now, briefly, that with a few assumptions, we can give some conclusion purely at the geometrical level. And so the question is, what are the assumptions and what are the limitations of this approach? Because of course, if I could say completely against instability, there would be magic. We don't know the dynamics of this theory. But we can say something that is still interesting. So the way we proceed is just to take this space-time, which is in vacuum is perfectly fine, and we add some perturbation. The simplest example of perturbation we can consider is just two null shells that we draw here that merge in a surface and give rise to two different null shells. This just divides space-time into a region, and then we take these two null shells and we make the crossing point closer and closer to the inner horizon. Now, a null shell is a very idealized sort of perturbation, so we may wonder whether or not this is realistic to consider it. And the answer is yes, but only close to the inner horizon, which is actually where we want to look at. Because close to the inner horizon, we have a strong blue shift, and so if I take something which does not look like a null shell because it's just very separated, the geodesics will focus at the inner horizon, and the width will be smaller and smaller, so this will look more and more like a null shell. You cannot take this perturbation and put it closer to the outer horizon because the space-time will prevent you from that. If you take something which looks very close to a null shell and try to put it closer to the outer horizon, this will just spread because of the redshift of the outer horizon. And then we just need to do the assumption that the asymptotic mass of the space-time is shifted across one single shell by a value proportional to the image of the shell. As simple as that. And of course, this may be violated if you have a theory of gravity which completely switches off with the reaction of a single shell. Then the space-time will not see any perturbation and nothing will happen. But as long as the space-time feels something which is proportional to the energy of the shell, then everything else is just follows from geometrical arguments. And what follows from geometrical arguments is that in this region in between the two shells, because of the strong blue shift closer and closer to the inner horizon, this quantity here is the Misner-Sharp mass, which is the important point of this fact is that this function that it directly enters into curvature invariance. This quantity here diverges exponentially as you approach the inner horizon. And this means that the curvature invariance diverges exponentially. So as you add a small perturbation, you will have a huge backreaction of the geometry. Now we cannot say what is the backreaction going to do because we don't know the field equations, but we can say that this is not the full story because as soon as you do a small perturbation, you will have a huge backreaction. Now this the Campagna structure considered before is an eternal geometry, and it has a lot of problems even without the instability. One of them is that we have a Cauchy horizon here. And the fact that we have a cushy horizon means that the initial value problem is not well defined. You can give initial condition in our current universe, and then you try to evolve it. Once you get to the cushy horizon, you need to give new initial conditions. And so this is probably worse than a curvature singularity. However, the same argument can be applied in space-time, which looks very different from the causal structure point of view, in which we introduce some time dependence, so this geometry is going to be time dependent, and describe something that is formed by gravitational collapse. It's formed by gravitational collapse, and it evaporates or anyway it dissolves in a finite time. So we do not have an event horizon here, but we have a potentially long-living trapping horizon. And we have a trapped surface, but not an inner horizon. And we do not have a cushy horizon that marks the end of the predictability of the theory. So this, from the point of view of predictability, this space-time is much better. And again, we can devise some geometry that does that, and we can study the perturbation, the consequences of the perturbation in this space-time. And we get basically the same result, although the assumptions are slightly different and slightly stronger actually, but we get essentially the same result. Here we have the outer horizon, here we have the inner horizon as a function of this advanced time b, and here we have some perturbation. The form of the perturbation we have to change it slightly. And you can see that this function here that enters the curvature invariance diverges again exponentially in a very short time scale. It does not reach infinity because it will eventually leave the top surface, but it reaches huge values. So we start with something order 1, we get 10 to the 7 in a very short time. And here we have a reasonably small black hole, but if you get something larger, which is a bigger separation between inner and outer horizon scale, this is even worse. But again, we can say that this picture, where this is a long-lived horizon, is not fully consistent because we have a very fast instability, very fast perturbation. What is the reaction of this stability? This requires the field equations. And this is, for example, a very recent paper where they study this problem, which takes some field equations. So we need to specify the problem. So you lose generality, but you can study the problem in more details. And they find that this trapped surface actually disappears very quickly. And you have a white, something that looks like a white zone very quickly. So this is kind of problematic for this object. Now, what happens when we are in this other region? We take this parameter, we increase it a little bit more, and we get rid of the inner horizon. So getting rid of the inner horizon is getting rid of the source of instability. Well, now we need to focus on something else, which are light fields, which are just locations of circular orbits. And if you have a systematic space-time, you can easily find them. I will skip these details. And we have in the Kerr space-time, we know that light fields are just subdot points of the effective potential. There are some results that tell us that horizontal objects must have an even number of light fields, and the inner one must be a global minimum of the effective potential. So the situation is something like this. You have this effective potential, you have one subdot point which corresponds to the light field in Kerr. You must have another one if you want to avoid singularity and horizon, which is a global minimum of the effective potential. Why is this interesting? Well, it's interesting because we definitely want the outer horizon in order to describe the physics that we observe. So the outer light, in order to describe the physics of the phenomena which we observe. But the inner horizon is believed to be associated with another source of instability. I will not enter into the details here, but the reason for this instability is that we have a global minimum of our effective potential, and we can imagine perturbing a space-time, and the perturbation will accumulate at that global minimum, and will in turn deepen this potential well, and this will lead to a non-linear instability. Although this is a very heuristic argument, there are only a very limited number of evidence, so there is still definitely something to work on, but it's believed to be universal. But again, there is only a very heuristic argument. And then, let me go back. Then the other possibility is that you are exactly here, where you have the extremal configuration, and this is also seems to be unstable. There are several works studying this, although they mostly focus on black holes in general relativity. So the question is whether or not there is any hope for non-singular objects. And well, yes, there is some hope, but there is still a lot of work to be done. And we have listed 3 points. So the mass impression stability for non-singular black holes, I would say it's quite well understood and also needs limitations. But any point of this stability is not clear. Also, it's possible to show that, at least at the classical level, there are some regular black holes without mass inflation, without this instability, and we are now working on a semi-classical version of it. But then the question is that whether this object that are very fine-tuned can be formed dynamically. Regarding the stable light field instability, so the objects that do not have horizons, well, this is not very well understood, because we only have some evidence, numerical evidence for a specific class of boson stars, which are actually fastly rotating, and the fastly rotating objects, even neutron stars, can be unstable because it's rotating very fast in order to have. So boson stars they're not super compact, so in order to have this light field pairs, they consider they consider a very rotating and for the general case, we only have realistic arguments. Furthermore, there are static boson star studies, recent studies, that do not show sign of instability, but it needs to be noted that in that case, the mean modificative potential is very shallow, so this probably it means that the time scale of instability is very, very long, so this is idea. So. And then going to the extremal black hole instability, as I said, it's studied only for singular black hole in GR, but it's studied for a lot of singular black hole in GR. There's a lot of type of perturbation, and it also seems to be quite generic. And I would say this is somewhat understood, but you should always read the fine print because it's even high things. And I will just make it larger just for you. And I say it's somewhat understood, and it's not understood by me because I have a lot of puzzles here, so this is why I didn't talk about a lot. But there are several papers here that is just a very, very incomplete list studying this stability. And in all of them, there is something that I don't fully understand. On the one side, I told you that, sorry if I go back and forth, that the inner horizon and the stable lighting are sources of instability. And in the extremal limit, they both converge at the single extremal black hole. So it's reasonable that you will have some problem there. But when you go into the technical details, there are a lot of things I don't understand. So there is still a lot of work to be done in these first 2 classes, and at least for me there is a lot of work to be done in third one because I need to understand it. And I would have loved to talk about observational signatures and talk a little bit about astrophysics that you can see in the paper some discussion. But of course I don't have time. I didn't expect to have time for this. Just in a word, I would say that observational signatures, even if you do something very smart and you expect to see something, they turn out to be more difficult than what you would expect. But and also there are problems in modeling astrophysics, and there is a lot of issues there. I will not enter into that. I will just go to the conclusion. So I will just go to the conclusion. I have, so I hope now you understand why I was insisting on this simple plot from the beginning, because even though this is the simplest, the very simplified scenario kind of encaptures what the information we were looking for. There's still a lot to do to obtain a valuable alternative to the codes. And I would like to say that this is actually a positive feature, so I'm actually happy about it. Because if you look at the literature, there are lots of models coming from a lot of different, there are a lot of consumer models coming from a lot of different vector models inspired by quantum gravity or something like that. You see that I tried not to use any specific model because the freedom is really unlimited. I tried to understand what can be the issues in the most generic way as possible, whether or not the geometric structure, the similarities among all of these models can tell us something meaningful, because otherwise we really need to look at any specific model independently. And also, we can always imagine deviations where the probability scenario where the deviation from the codes are all in a tiny region inside the object, and this will definitely mean that we will never see anything. But if we see from universal features and we see what are the problems, this can help us navigate this predator model. And in particular, if I go back one last time, so let's go back and forth, I mentioned, at least in my mind, that the instability, having a linear horizon is the one that is better understood. And this one related to the object that has the least hope of having observational features, almost zero hope to have something that can be seen from outside. So either we address these issues or we might have some observational signatures. Then of course I'm not going to say we're definitely going to see it, because I know that this is going to be extremely difficult and probably maybe impossible in practice, but given the theory is giving us that it's breaking down there, we can investigate this issue, and we need a lot of theoretical work yet to tell us where we need to look for modifications. And also here, I leave the questions that you can find again in this paper, and especially for the students in this topic, this is a good reference. And as I said, I just selected very few of them, but I think there is a lot of interesting things to say about all of them. Thank you very much for your attention.
We have time for a couple of questions.
Thank you, Francesco. So, regarding the curing the singularity with an inner horizon, I slightly disagree with you in the sense that you said we don't know the field equation.
No, we know, we don't know, like, we have a lot of examples of different field equations that give us this.
Well, what I mean, because you are doing static solution, no? Stationary solution.
Well, yes, most of them. I also show something non-stationary.
Well, what I think one should do here, it would be very interesting, is to do, because the inner horizon is an intrinsic property of a gravitational collapse.
Yeah.
That disappears within the singularity at the end of the collapse.
Yes.
So, but you can cure that if you violate the energy conditions, then you can avoid this. But then, of course, you have to study if this is going to be a stable solution. So, my suggestion is something actually I've been talking with Stefano in the past. It would be very nice to understand what would be the violation of energy condition, which is in practice related to quantum effects.
Mm-hmm.
And then if these solutions are unstable, I think this dynamical approach would be the right way to look at this problem.
So I absolutely agree. The only problem with that is that, this is important because you always need to complement these generic things that are independent of the field equations with some specific field equations. You have a lot of freedom, but again, eventually we need to do that. But it's interesting to push as much as possible the geometrical arguments, because this will be applicable to
yes,
all.
but that's the equation are geometrical to matter, so if you just look at the left-hand side of it and the right-hand side.
No, I completely agree. So you cannot go all the way, but I was just discussing what you can say that is going to be generic. But then I'm also at the moment we're discussing things related to some specific model and see what's happening. And I also had one reference I added here. I mean, there are several people working on this. Like here they look at resonant notion of black hole in semi-classical gravity, so they have some well-defined equation of motion. It is singular, but they take a foliation so that you don't see the singularity. And they consider basically the nonlinear particles because they gravitational collapse and they see a bounce into a white hole. So this has to be done. And but it's not what I want to say. It's not an alternative. It's just complementing what I was saying. Yeah. But it has to be done. I agree.
Nice.
More questions?
Hi, thank you for the talk. I know you don't have time for it, but could you maybe comment a bit on the observational channels that are maybe most promising, or what the current state is, or how one would start from things?
Yeah, so observations, it's definitely very difficult because even if deviations on the horizon scale, they're not really probing the horizon size with observation. We're probing something that's close to the photosphere. There was some channel that it was very clear, something like that was supposed to be. It was nice, a very nice idea. The fact that these objects are not in vacuum, but there is a lot of radiation going in. So if you imagine that this object will have a parallel surface, eventually they will start emitting thermal radiation. And there was some initial analysis discussing this possibility, and initial claims that we were going to rule out a lot of models. But the problem is that as soon as you add some absorption, so imagine if you have this accretion disk, stuff accreting onto this horizontal object. If you assume that this is going to absorb even a small fraction, you will avoid all the constraints that you will cast. So this is one possible channel, but it's so look at once these objects are you radiate enough energy into the objects and you look at what they emit. But unfortunately, they emit even less than what you would expect. This is unfortunate, but you can cast constraints, but they are quite good. We can discuss later what this plot means if you want.
Okay, thank you.
More questions? Okay, down to the stand again.